Alright, before I go through this problem set, and I'll be posting them out, showing you to do them a number of ways, from start to finish, I want you all to realize that essentially there's been just two forms of problems, and that was concurrent force problems and non-concurrent force problems. In other words, a lot of statics is just learning which of those two to apply in what collection of ways as you cut up free bodies into different smaller free bodies and solve for internal forces, eventually stresses, or external reaction forces. And so what I'm going to do finally now is I'm going to go through and give you in 10 minutes, keep to that, what you should start to believe, and then figure out how to use your calculator, how to sketch, and especially how to mix AutoCAD or SketchUp in there to get you through some of these kind of tough parts of trigonometry until in the end you go back to the trigonometry. I'm going to do that by talking now about, with my start inking here, my ball pen, I'm going to try to write relatively well. I'm going to talk about at this point, of course, first concurrent force problems. Concurrent force, just addition. Concurrent force addition means that if you have a vector here, and a vector there, and a vector there, the next step is to make it a star diagram, and so that's basically to take this and push it out to there. Sorry, it should be a little bit better. And then to what? Go ahead and I'll try to sketch it out here. Say you're beginning at 0, you're adding this force, and then you're adding this one to it by sliding a parallel vector, and then you're adding this one to it as well, and what you have then is the resultant. So if you are doing concurrent force addition, that's how you do it. If you're using subtraction, you add the opposite vector. So if this minus this is the same as this plus this, which of course becomes this and that's how you go about doing concurrent force subtraction. Subtracting is opposite of addition, or adding the reverse, adding the opposite. And I just had a conversation with a retired military guy, said guy being my principal at my kid's school, and immediately he knew what the opposite of 180 was. He knew it was 0, even without knowing, right, what reference system we're in. So you have to realize that the opposite in an angular system is plus or minus 180, and the opposite in a vector system, let's say this was maybe 2i plus 7j plus 6k, the opposite direction of that, or the opposite vector, is minus 2i minus 7j minus 6k. So understanding how to do opposites and how to add forces up into x, y, and z. I'm going to go down to the next slide, and we're going to now talk about not just concurrent force addition, but concurrent force problems, where generally the most common form is two known directions, two unknown magnitudes, and then a collection of knowns. In other words, you can have, let's draft it here in the right direction, let's an unknown force 1, in a known direction, an unknown force 2, and you might have these three things, each being knowns. That problem turns out to be basically this problem, and then immediately you add these vectors, and if you think about it, that vector goes here, here, and there, And so what you end up knowing is that if this is F1 and this is F2, that these have to be the opposite. These two have to add up to be the opposite of that, and how that looks mathematically is this. F1 times the cosine of the direction of 1 plus F2 times the cosine of direction of 2 equals the opposite of the known f of x's. And on top of that, F1 times the sine of theta 1 plus F2 times the sine of theta 2 equals the minus, that's a minus or opposite, of the known f sub y's. In a matrix, the matrix you make, and you can immediately start doing that, would be just this, the cosine of theta 1, the cosine of theta 2, and then the opposite in here. So then opposite of known f of x's. And then the sine of theta 1, the sine of theta 2, and then the opposite of the known fy's. You use the RREF and you solve immediately for F1 and F2 and you're done. Even easier than doing it by sliding vectors, I would say. I will let you know that this works in 2D or 3D. But then, of course, going to 3D, you have to remember that your z's are going to be the magnitude times the sine of the elevation angle. And your x's are going to be the magnitude times the cosine of the elevation angle times the cosine of the angle in the xy plane. And your y's are going to be the magnitude times the cosine of the elevation angle times the sine of theta. But it works out to be the same way. Those are concurrent force problems. Now on to non-concurrent force problems. First and foremost, this is coming back at you, right? If you're adding up 3 non-concurrent force problems or 3 non-concurrent forces, the way to go about doing it, to always do it, is calculate the sum of r cross f, right? With these, of course, being the radial vectors, and then dividing it by the sum of the forces, right? And that will get you the length of the moment arm, basically. But what we can do in this case is, let's remember that we can daisy chain. So what we can do in this case is we can add these two together by basically going and assuming that the point of concurrency is here, right? So we can go ahead, we're going to move that one to here, and then adding this one, right? So now what you have is a resultant of those two, and then hopefully eventually you could see that these two, right, add up together and you can slide vectors. So non-concurrent force problems can be daisy chained. All right, and of course we know they can also be done by solving the sum of r cross f, which is just, of course, the sum of, that's going to be the moment, and of course the sum of the forces, and you can use those two then to determine where that line lies, because this basically will get you the magnitude and direction, and this divided by that will get you the moment arm. Now that said, with a minute left, let's see where those come in. In a truss, you've just drafted one. 1, 2, 3, 4, 5, 6, 7, 8 if you think about the members. 1, 2, 3, 4, 5. Let's say you have all these members here. You'd solve for your reactions. And you have to remember that you can cut this here. In this case, if you cut this there, you have a method of the joints. And if you cut it, if you think about the sum of the forces about this point, and if you do it this way and replace this and this, right, or better yet, cut it here, you replace this, this, and this with these forces. If you pick this point, what you have is a force times distance equals a force times distance, and you have a non-concurrent force problem. The reality is you'll use a mix of the two. That's essentially what we've done up till now within strengths. We'll see now how much we can leverage that going forward.